is Ruihan. I'm presenting our work, Learning Vision-Guided Quadrupedal Locomotion end-to-end with cross-modal transformers. While learning-based locomotion has made great advances using RL, most methods still rely on domain randomization for training blind agents that generalize to challenging terrain using only proprioceptive state of the robot. For example, the work here shows interesting results on challenging terrain. However, the robot is running without vision. However, when maneuvering environment with obstacles and a challenging terrain, proprioceptive states only offer contact measurement for intermediate reaction, whereas an agent equipped with visual observation can learn to proactively maneuvering environment with obstacles and uneven terrain by anticipating the changes in the environment many steps ahead. In this work, we introduce local transformer and end-to-end RL method for quadrupedal locomotion that leverage a transformer-based model for fusing proprioceptive states and visual observation. Our model takes proprioceptive state and visual observation as input and output the action distribution or value for policy learning. For information from two different modalities, we use two different domain-specific encoders. We use an MLP to encode the proprioceptive state and then ConvNet to encode the visual observation. We then convert the feature from different modalities into tokens. We treat proprioceptive feature as a single token and split the visual feature into multiple visual features, the visual tokens that each corresponding to a local visual region. After getting tokens, we perform multi-layer self-attention on proprioceptive and visual features, enable our model to fuse the tokens from both modalities at multiple levels of abstraction. We then get a single feature vector for each modality, concatenate these features, and project the concatenated feature into a final output using a projection head. Here, we'd like to show what our method learned. Here, the agent is moving forward in the environment with numerous thin obstacles moving in random directions. We can see that agent learned to predict the movement of the obstacles and take a detour to avoid the potential collisions. We also evaluate the generalization ability of our method by transferring the policy trained on environment with thin obstacles to unseen environment with chairs and tables. We can see that even though the agent never sees chairs or tables during the training, it can still understand the semantic meaning of the objects and avoid them. We visualize the self-attention weight between the proprioceptive token and all visual tokens in the last layer of our transformer model. We plot the attention weight over the raw visual input, whereas the warmer color represents a larger attention weight, and the agent learned to automatically attend to the critical visual regions for decision making. Here, the agent is attending to the obstacles in front. And here we can see the agent attend to the high slope terrain in the left figure and the goal location in the right figure. Now we'd like to show some training and evaluation results. For environment with sphere, as shown in the curve, our method achieved better final performance and also sample efficiency. We also evaluate the generalization ability of all methods by evaluating the policy on unseen environments. From the chart, we can see that the collision with obstacles significantly reduced with our method. Thank you for listening, and our project page is provided here for more details and results.
Yeah, thank you, Ruihan. Any questions from the audience? Maybe one quick question of what's the action space of the reward in your method?
In our method, the action is basically the angle of all joints for the robots.
Okay, so what's the reward?
The reward is basically moving forward without collide with obstacles, and you can see there are some spheres in the environment as well. If the robot collects some sphere, it will get some extra bonus because we add those sphere to see whether the agent can distinguish the objects using with different semantic meaning. Yeah.
Yeah. Thank you. Any questions from the audience? If no, let's thank Ruihan. Yeah, thank you.